all the people who have recently joined, kindly turn on your cameras. And Lenin, we can start within a minute, I guess.
Okay, fine. So, hello everyone. Good evening. I'm very excited to have all of you here. Myself, Lenin Kennedy. I'm a third year student from VIT Chennai, and I'll be your host today on behalf of SEDS Antariksh. So, so I'm very excited for this evening, and we have people from VIT Chennai as well as BITS Hyderabad. So, before we start with the session, I'll just have take 2 minutes of your time and just introduce what is SEDS Antariksh and what do we do over here. So SEDS Antariksh is the only space chapter here in VIT Chennai, and we work on spreading awareness about space and astronomy and participate in competitions as well. So right now we are working on some very interesting projects, and so this topic is very very relevant for us, I'd say. So, yeah, let's get started. Atreyi, are you there here?
Yeah, I'm here.
Yeah, so you could introduce yourself and we'll get started.
Sure. Okay. Hello, everybody. I am Aatreyi Dasgupta. I am an undergraduate in BITS Hyderabad. I'm currently in my third year. I have been very involved in the field of astrophysics as I'm planning to pursue my PhD also in astrophysics. And I have also taken part in various competitions such as International Astronomy and Astrophysics competition, where I received the silver honor. I have also worked in various projects such as the Kritika Summer project, which is held in IIT Bombay, and I have extensively worked in radio astronomy there. And this talk is very heavily inspired by a talk I heard in the project, which was given by Dr. Alessandra Corsi, who is a very renowned physicist in her field, which is multi-messenger astronomy. Thank you. Yeah.
That
Go
sounds
on.
great, Atre. So let me tell something before we start, okay? Atri, like as far as I've known for like few years, she has been very passionate about space, and that's how you see her passion in like doing her masters in BITS Hyderabad and also pursuing for PhD. And also this session is gonna be really good. I'll say that.
I
So
really hope so.
yeah. So you could get started, Atre. You could just give a brief of what we are gonna do and get started. I'll give
Sure.
it to you.
All right. I'll just share my screen. Uh, Let me know if you can see the screen.
Yeah, it's visible.
Yeah. Okay. Thank you. All right. So, hi. As I've mentioned before, I am Aatreyi and I'm an undergraduate in BITS Hyderabad. First of all, I would like to thank the SEDS Antariksh Club for giving me the opportunity to give this talk. So, as I've mentioned, I did a summer project under Kritika Club in IIT Bombay. They are the astronomy and astrophysics club of their college. And yeah, so this talk is heavily inspired by Alessandra Corsi. I remember seeing her talk and getting actually very inspired to work in this field further. So let's begin by discussing what we will learn in this talk. So essentially, I will start by explaining what a neutron star is and what does it mean when I talk about neutron star merger. After that, we will go into the field of multi-messenger astronomy, and we will go very deep in what a neutron star merger is and the kind of emissions that a neutron star merger give out, etc. I will end this talk by discussing very key questions such as so the neutron star merger we are going to talk about today is the GW170817. And actually, we were off axis observers. So when the neutron star merger happened, we were 20-degree off axis, and yet we were able to see radio emissions, we were able to see X-ray emissions. So we will discuss how that is possible, because intuitively it does not make sense because we were off axis. And we will also discuss the prospects of this event. I really hope you guys enjoy this talk. Also, I would like to discuss why this talk is beneficial for people who are not directly involved in the field of astrophysics. So, when you understand about this event, you will see that there are a lot of people who are involved in various fields of STEM who all are involved in this single event. So this event doesn't really just consist of astrophysics, but it also involves heavy data analysis. It involves nuclear physics, it involves particle physics, it involves X-ray studies, it involves radio emission studies, etc. So the motivation behind this talk is also to provide you insights about how not just astrophysicists study the celestial events that happen in the universe, but how people from different fields in entire STEM come together and study one single event. I hope that you guys do enjoy this talk, and we shall begin. So let's talk about neutron star. So what is a neutron star? So essentially, also just we can just reserve the questions for the end of the talk, and you guys can post it in the comments, I guess. But I'll take it after the whole session. All right. So what's a neutron star? So neutron stars form after a supernova explosion, which is near the end of the life cycle of a star. So essentially, after a supernova explosion, the core of the star remains, and what will happen after that depends on the mass of the core. So essentially, neutron stars are mainly composed of neutrons, as the name suggests, and are incredibly dense. So essentially, when a supernova explosion has happened, the core remains, and if the mass of the core is relatively equal to the mass of the sun, or maybe slightly more, the star system, collapses to form neutron star. So as you can see here, this is the neutron star merger event, the GW170817, which we'll heavily discuss today. So this right here is the neutron star merger event, which this is the scale relative to the mass of the sun. So this says that this is of the order 1 m naught being the mass of the sun. And in the right panel here, you see two black holes. So how does a black hole form? So when the mass of the core of the star is maybe more than 5 times the mass of the sun, then the system collapses into forming a black hole instead of a neutron star. So this right here is the collision of two black holes. And interestingly enough, this GW150914 event, this was the first time that we actually detected gravitational waves. We will discuss extensively about gravitational waves too. So I'm just going to put a pause here. So interestingly, we don't there's a big question mark about what comes after neutron star and before black hole. So we only know the approximate value of the mass of the neutron star, not the exact limit. So we don't know the maximum limit of a neutron star. That is mainly because of the uncertainties of the equations of state of nuclear matter, which we will not go into. But yeah, it's a very big question mark. And yeah, so let's just discuss how this naming is done. So here GW stands for gravitational wave, 17 stands for the year, 08 stands for the month, which is August, 17 stands for the day, so 17th August 2017. Similarly, this is 14th September 2015. So let's just clear some jargon away. I'm going to keep publishing I'm going to keep showing this slide over and over again so that you guys get comfortable with the technical terms. So we discussed what a neutron star is. It's a highly dense celestial object formed after the collapse of a massive star during a supernova explosion, and is composed mainly of tightly packed neutrons. Yeah. So now let's discuss about gravitational waves. So in simple layman terms, gravitational waves are ripples in space-time produced by massive accelerating objects. What are massive accelerating objects? So massive accelerating objects are essentially colliding neutron stars or colliding black holes, which we saw in the earlier case. both of which events produce heavy like gravitational waves. So interestingly, even though the first detection of gravitational waves was done in 2015, Einstein back in 1916 predicted the existence of gravitational waves and also predicted that the gravitational waves propagate at the speed of light and carry informations about their origins. Let's just take a moment and observe this simulation. So this is a simulation of two neutron stars spiraling around each other about to collide. So if you can see, these are the waves that are propagating away from the source. This in simple terms is what gravitational wave is. Like this is what it signifies. So essentially, these are the gravitational waves. They are coming out of the source, and these are spiraling towards each other. The frequency is increasing of the waves, as you can see. The waves are speeding up, and and it merged. Yeah. Yeah. So essentially, as you see, one key thing is that the gravitational waves come out of the origin from the source, and another very important aspect is that to make you understand this, the gravitational waves are showed in this simulation, but very obviously these are not like visible. So gravitational wave, you can feel the gravitational wave intensity, but obviously you cannot see gravitational waves for yourself as they are ripples in space time. This will become very important in the further talk. Wait for it. Yeah. So this in the left panel, this is a two-dimensional illustration of how heavy accelerating mass in the universe distorts the space-time. So as I mentioned, and I like to go over it again, when was it first discovered? When were gravitational waves first detected? So the first detection of gravitational waves was done on September 14, 2015. So LIGO stands for Laser Interferometer Gravitational Observatory. So LIGO sensed the undulations in space-time caused by the gravitational waves generated by the two colliding black holes that we saw before. So these colliding black holes were actually 1.3 billion light years away. All right. Now that we understand what gravitational waves are, we understand how it comes. Now we will go into multi-messenger astronomy. Let's start by discussing what multi-messenger astronomy is. So as the name suggests, multi-messenger astrophysics involves analyzing celestial events at least two different signals. So essentially, generally the two different signals are electromagnetic waves, which we know as light, and gravitational waves. So even in this event, the GW17017 event, the neutron star merger event, we observe the merger event with these two signals, electromagnetic waves and gravitational waves. So one natural question is, why do we need two signals? Why can't light be enough? Like, why do we need the extra hassle of gravitational waves? There's a very good reason for that. So essentially, light cannot go inside the very compact regions of the universe. So as we know that neutron star merger, black hole merger, etc., are very compact objects. They are very dense. They are very compact regions of the universe. So light can sort of go around the region, but it cannot probe inside the region, which is why we need gravitational waves to understand the kind of ejectas which are coming from the neutron star merger, how the neutron star mergers are spiraling around each other. And the beautiful part about it is, if you study the event in both electromagnetic waves and gravitational waves, you can kind of see the dance that the neutron star the two neutron stars do while they are spiraling around each other and are about to merge. So let's analyze what is going on here. So this is what we believe happens when two neutron stars merge. So neutron star merger. So this black thing that no, you can see the black dot here. This is the smash up region where the smash up happened. So neutron star mergers, as you can see here, can result in material ejection, like which can take various forms, such as the relativistic jets, which you can see the black jets that are flowing away. It can result in accretions disk, which you can see here. It can also evolve in like it can also eject in like spherical outflow, which you can see here. These are the spherical outflow. So this is the blue ejecta, this is the red ejecta. So these ejected material, this spherical outflow, emits thermal radiation, which is known as kilonova, which is observable in UV, optical, IR over hours to even days. So we will go into this in very much more detail, but just to give an overview. So the blue ejecta here, you can observe the blue ejecta. At least researchers observed the blue ejecta from this neutron star merger to 5 or 6 days. But the red ejecta was observed for over maybe 15 days or 20 days, which is like in the span of weeks. So it's very interesting, and we will go into this later. Now, let's talk about gravitational waves and how gravitational waves are detected. So, obviously, gravitational waves are ripples in space time. So, very obviously, they cannot be detected by general telescopes, which we use to detect radio emissions, X-ray emissions, etc. So, gravitational waves cannot use telescopes. So, what can they use? So, we know that gravitational waves can be detected by measuring the gravitational wave intensity. So, we need kind of a detector to measure the intensity. So, the way to go about is to use an interferometer. So, let's first discuss what an interferometer is. So here you can see in this panel, so this rectangular sort of thing that is here, this is the source from which laser beam comes off, or maybe light comes off, whatever you choose. So this is shown by laser. So generally laser is used. A laser beam comes off. This is a beam splitter. If I don't know if you can see, but there's a slanting thing here. So this splits the beam into two different beams, which goes off in perpendicular directions. So these go into perpendicular tubes rather of the same length. At the end of each tube, there's a mirror. So essentially, the beam comes from here. It goes to a splitter. It goes here and here. It bounces off the mirror. It again travels the same distance. Recombines in the same beam splitter, or recombines at the base. Goes here where there is a small detector here, which detects the intensity essentially. So if you can intuitively understand, if the lengths are same, if the perpendicular tubes have same length, there's phase cancellation, right? So because both of the light are in same phase, so you will not be able to detect any any light. But now this is the key factor. So this was done in the absence of gravitational wave. Let's say gravitational waves are involved now. So gravitational waves, as we all know, distort space, which this is very interesting. So gravitational waves distort space, and it leads to one arm being slightly longer than the other. And then there is an immediate switch, causing this arm to be longer than this. So this continuous switching of the lens, obviously, then these waves are not in phase. So these waves do not line up. So it causes this. The waves are not lining up. So basically when there's a passing gravitational wave, this results in the waves not lining up. Detector, which is this, the detector measures the intensity of the gravitational wave, and that's actually how gravitational waves are detected. So it's a very easy process, but of course, like in our real world, these two perpendicular tubes are actually two perpendicular roads which go off like kilometers and kilometers wide. So yeah. Now let's just go into a little bit of math, not a lot. So this right here, this H is the strain, or you can say this is the amplitude of the gravitational wave. So let's just ignore these for a minute. So the amplitude h, as you can see, is inversely proportional to d. So what is d? D is the distance from us to the source. So from observer to the source, d is the distance. So why is this important? Is because this scaling sort of allows for improved sensitivity while you are observing distant objects like colliding neutron stars or colliding black holes. So this is really cool because uh, you know um, further the objects are, further the massive accelerating objects are, the better sensitivity you'll find while measuring the amplitude. So which is an amazing thing. Which is why, if you remember, 1.3 billion light years away, which is quite far. So 1.3 billion light years away, the two colliding black holes were actually the first time we measured gravitational waves. Yeah. So again, let's just clear out some jargon. So now we discussed about gravitational waves, which are like ripples in space-time, which are produced by massive accelerating objects such as colliding black holes, colliding neutron stars, supernovae, etc. We talked about multi-messenger astrophysics, which involves analyzing celestial events such as the merger of the neutron stars by at least two different signals, which is right now light, and which is the electromagnetic wave and gravitational waves. We also studied about neutron star mergers, how neutron star mergers can result in material ejection, which takes various forms such as relativistic jets, accretion disks, and spherical outflow. We also discussed about kilonova. So kilonova is essentially release of neutron-rich debris. So this is important. I would want you guys to focus on this because this will be heavily used in the next slides. So what is a kilonova? I'll just pause and explain it a little bit nicely. So when there's the merger, when the two neutron stars merge, it ejects material, right? So one of the ejections is what we call as kilonova. So these basically this ejection has neutron rich debris. What it means is the ejection have a lot of neutrons. So a lot of neutrons form heavy elements, right? So it can form very heavy elements, very heavy radioactive elements. So these heavy elements, slowly as time passes, these heavy elements radioactively decay, and because of this radioactive decay, it sort of heat up the matter surrounding the material, which which is like an afterglow, like which glows up. So which is that is what actually we call as kilonova. So this glow up, because of the radiation, because of the heating up of the matter, because of the radioactive decay of the neutron rich debris, is what we call as kilonova. I hope that's clear. Now let's come into the much awaited event, GW17017. So this was a neutron star merger event, which was, if I'm not wrong, which it was around 130 million light years away, which is actually not very far away in terms of astronomical scale. So we were kind of lucky to have it like a little bit closer to us. So GW17017 was a neutron star merger event which initially produced both gravitational waves and gamma rays. So you can see here. So this lower panel is the gravitational wave panel. The upper panel is the gamma ray burst panel. So as you can see, the frequency increases. The frequency of the gravitational wave increases, and it reaches a maximum, which we call as the gravitational wave chirp. Now, roughly about 2 seconds later, you see a sharp gamma ray burst. If you can see this, and then it's again back to normal. So let's discuss a little bit in more detail about what just happened here. So in this lower panel, let's first discuss this. In this lower panel, this is a time frequency map. What that means is the x-axis is the time, y-axis is the frequency. If you remember the simulation that I showed earlier, so when the two neutron stars are spiraling towards each other, you could see the frequency of the gravitational waves was increasing. So as and when the neutron stars were, like spiraling around each other, and the basically they were spiraling closer together, the frequency of the gravitational waves were increasing. So that's what we see here. This actually gives us a direct proof that we were right. Our hypothesis was right. So this right here is the increase in the frequency of the gravitational wave. So this shows that the two neutron stars were spiraling faster and faster towards each other, and obviously it reaches its maximum at the time of the merger. So this line that you can see right here, the gravitational wave chirp, so this represents the time of the merger, which in physics we call as the time zero. So time zero is whenever some event happens, basically. So this is the time zero. And let's say the x-axis is in terms of 1 second scale. So the scale is like 1 second. So you see approximately 2 seconds later, or like maybe 1.7 seconds later, you see a sharp gamma ray burst. So I remember when I was attending Dr. Alessandra Course's talk, she referred, intuitively, she referred that you can understand this map in the form of musical notes. So you know how each musical note can have a different frequency attached to it. So as the musical note goes on, the frequency changes. So if you have to enact this like in a musical tone, this graph right here will go as a whoop. Like from, if you could see what I did there, the frequency just increased and the pitch increased and reached at a maximum. So essentially this was how gravitational waves were detected. Now coming to the upper panel, the gamma ray burst. So how am I saying that both of these both of these emissions or signals came from a single merger event? How am I so sure? I am so sure is because this is so gamma ray burst is no news. Like we always knew that the gamma ray burst generally, if you catch a gamma ray burst, then it is most likely associated with some neutron star merger event. So this happening in such like close proximity, the time proximity, confirms that both of these signals came from a single merger event, which is the GW17017. So the next step was for the scientists to detect where this event happened in the celestial sphere or in the sky. So this is the celestial sphere. So this is the Fermi satellite, which was responsible for seeing the gamma ray burst. They said that the location of the sky was approximately this. Then there was this integral satellite, which is an independent satellite which said that the emissions came from this patch of sky. And then there was LIGO, which said that the emissions came from these two narrow strips of the sky. So this the really the intersection of all these regions is just this narrow strip. So obviously the next step was to find what celestial objects are in this patch of sky. So while the astronomers were observing, they saw that the galaxy NGC 4993 was actually in this patch of sky. So this patch of sky is roughly 40 megaparsecs away. So you can see that this picture was taken on April 20, 2017. There's no, then the picture was taken after 11 hours on August 17, 2017. So you see there's a black dot here marked with the red arrow, but there's no black dot here. So this actually is the direct proof of the optical afterglow. So this is what we call as the first optical signal that is associated with the GW17017, because this was first detected near the galaxy NGC 4993, and this was first detected 11 hours after the merger event took place. So obviously this optical emission, as all emissions do, the optical emission faded over time, and you can see that this is what I was talking about earlier, the kilonova. So essentially the optical emissions is what powers the kilonova. So essentially the kilonova was neutron rich debris formed which forms heavy elements which radioactively decay and heats up the matter. So you see the blue color spectrum ranges for just few days, And by the way, the y-axis is the apparent magnitude, and the x-axis is the time. So the blue color spectrum ranges for maybe 5 to 7 or 8 days, and the red spectrum can be observed to even as long as 20 days or 17 days. So that is what we observed with our afterglow optical signal, which faded over time. Now, follow-up observations were made in X-rays, radio, etc., and our main focus will be in the radio emission. What happened in the radio? So, I would like you guys to wonder for a minute that what can be the possible reason that we are observing optical after 10 after 11 hours, the kilonov after 11 hours, then after a week we saw x-ray, and after 2 weeks we saw radio. So why are there delays? Why can't we see all the emissions at once? So there's a really cool answer to that, which I'll cover in the next slide. So let's first discuss the radio emission. So let's look at this picture right here. So this is what we believe to happen when two neutron stars merge. So this yellow fuzzy dot that you see right here. So this yellow fuzzy dot is the location where the smash up happened, which causes neutron-rich debris going out, which causes to form heavy elements, causing radioactive decay. And radioactive decay heats up the matter, giving off an optical glow, which is the orangish glow that you see right here, the dynamical ejecta. This is the orangish glow. Now, unlike this, so this is what we call thermal ejections because there is heat involved, etc. So, unlike this, the radio emissions or the X-ray emissions, both of these emissions are non-thermal emissions. So, how are they non-thermal? They are non-thermal because they are produced by accelerating electrons. So, this relativistic jet that you see here in the aqua color, this is the jet core. Basically, what this means is that the high speed emissions were channeled in this cone that you see here, blue jet, a blue aqua color cone. Now, thanks to our radio observations, which we will see in maybe 2-3 minutes. So thanks for the radio observations. We also know that all the ejecta was not uniformly enclosed in this cone that you see here in the aqua color. So there were radio and X-ray emissions which were leaked out from the cone, which you can see in this dark blue region, the jet wings or the cocoon region. So this material was not as fast as this jet core, but obviously is coupled with enough energy so that you can see the radiation from it. So to get a better understanding, to get a better intuition with what's happening here, let's just sit inside the jet wings or the jet core and understand what's happening. So let's say you are inside the jet wings and the jet core. So you see this is where you are, and you see there are protons and there are electrons which are engulfed from the interstellar medium that's there, and these all are engulfed inside a shock. This shock coming from this jet front, obviously. So this shock is basically the radiation or the emission is accelerating, right? They are going in relatively very fast speed. So due to this acceleration, you are also, if you have to sit inside it, so you are also accelerating. So you see around you, the electrons are also accelerating. So the lighter electrons which are accelerating, they essentially give off electromagnetic radiation, so which is light. Now, the important factor to understand here, and this may get a little bit technical. So here there is gamma, if you can see. So this is what we call as the Lorentz gamma factor, which comes from special relativity. So in very simple layman terms, Lorentz gamma factor is associated with how fast these particles are moving. So essentially what it means is that if the radiation is going very fast, the Lorentz gamma factor is higher. If it's slower, then it's slower. So Lorentz gamma factor is basically directly proportional to the speed of the jet. Now the key question. Let's answer the key question. So I've said that the radio emissions and the X-ray emissions, etc., are enclosed in this. Like the most of it, the higher speed jets are enclosed in this jet core. But I'm not sitting here. So if I have to sit here in the central axis, then I'll be able to see the emissions immediately, like initially. But let's say you are this little guy right here. So you are an off-axis observer. In fact, we were off axis, we were 20-degree off axis. So how are you still able to see the emissions? How is it possible? So to understand that, let's take a quick look at what this is showing. So this essentially, this cone is the jet core that you see here. So this cone has, heavy speed, highly speeding, accelerating jets going on inside here. So this is something that I would want you to take for granted, because then we have to go into a lot of math to understand. So this angle right here, the cone angle, the solid angle of the cone. So this cone angle is inversely proportional to the gamma factor, the Lorentz gamma factor. So as we have discussed, the Lorentz gamma factor is directly proportional to the speed of the jet. So let's say you're sitting right here in this small segment. So obviously, initially the speed is really high. The jet is heavily accelerating. So obviously, the angle, which is inversely proportional to Lorentz gamma factor, and Lorentz gamma factor being directly proportional to the speed, the angle will be very small because of the highly accelerating jets. So here, let's say the Lorentz gamma factor is in the magnitude 50, about the magnitude 50. Then you see the cone is very small. The emission which will be channeled inside a cone is very small because the angle will be very small. But as every emission goes, the jet slows down or decelerates. And when the speed decreases, the Lorentz gamma factor also decreases because they are directly proportional. So as and when the Lorentz gamma factor decreases, the solid angle of the cone increases. So actually, you're actually sitting here. So you can see that as time passes by, that's why, and this is very important. That's why we see the emissions later. That's why we see the radio and X-ray the emissions later. So as and when the time passes by, the size of the cone, or maybe the field of view increases. And when the gamma factor has reached almost 3, you can see, you can just begin to see the radiation. So obviously, if you have to see the radiation at its full speed, or rather at its full frequency or full flux density, then you will have to be aligned with this central axis. So let us actually understand what happens. So essentially, this is our radio emissions. So let's say that we have to track the radio emission as a function of time. So this x-axis is the time. Also note that it's in the terms of years. And the y-axis is flux density, but for now, you can say that the y-axis is like the brightness, the magnitude of brightness. So if you see the graph carefully, you can see that there are blue highlighted regions here in the early time. So this blue highlighted region, you can sort of map it to the jet wings here, the blue region here, and the aqua color region where the peak is happening, you can map it to the jet core, and the light gray or like light blue color, you can map it to the dynamical ejecta tail. So we will get into this in some time. So this blue region here, which is mapped to the jet wings, so you see there's a slow increase of the light curve. So this is a light curve. So this light curve is basically a function of brightness light curve is basically brightness as a function of time. So you see a slow rise here, and you see a peak here, and you see then obviously after a peak, after it has reached its maximum speed, it will decay, it will slowly decay. So what does this light curve mean? So I'll just take 5 minutes and make you guys understand what this signifies, which is very important to understand how radio emissions work. So you see this right here. So this slow increase, it's very important to notice that this is starting from around 10 Nugensky, which we'll ignore for a while. So this is starting from 10 and not 0. So what this means is that when researchers saw that the light curve is starting from 10 on the y-axis, they understood that the emissions cannot be channeled in a very uniform cone, because to observe some radiation, like, because this is not zero, right, you are observing some radiation, some emission, it means that there has to be radiation leaking away from the jet core. So these jet wings are in your field of view. This cone, however, is not. But these jet wings, which we talked about, which are like slower moving emissions, these are in your field of view. So this is essentially what you're seeing here. So just by looking at this curve, just by understanding that this is starting from 10 maybe, you can actually understand the structure of the neutron star merger. So obviously, if there were no jet wings, then the dotted line that you can see, this starts from 0 and it steeply increases. So this is what you would see if there were no jet wings. So now you see that this is slowly increasing, and it reaches its peak when the field of view is aligned with this jet core. Basically, when the relativistic jet speed has decelerated, and that's when you see the radiation. That's when you see the radiation at its brightest, like at its at its brightest. So that's when the light curve emission peaks, like as a function of time. Now, obviously, after a peak, it will obviously decay because you're moving away, and like the cone is moving away. So it basically decays, and maybe for some other very off-axis observer, at that time there will be a peak there, but you will see it as decay. I hope that's clear. Now, the very obvious question that comes to mind is why are we still observing the light curve? Like, what's the use? So, we all know that it's going to decay, right? The light curve you see here is decaying. So, why observe a decaying light curve? We all know that it's going to like go down. So, there's a very interesting reason why. So, as you can see here, the dynamic ejecta tail, so this comes from the kilonova. See, the dynamical ejecta, which we said kilonova, which we said as kilonova. So essentially, the idea here is because we don't from here we cannot understand the structure of kilonova, because kilonova is a thermal radiation and this radio is a non-thermal radiation. So we can assume that maybe the dynamical ejecta, some part of it may be at a higher speed than the other parts of it. Maybe kilonova is at a lower speed, and the some part of the kilonova or some part of the ejection may be at a higher speed, which we see as a dynamical ejecta tail. So to understand this better, so this is the dynamical ejecta tail shown in gray color, and these blue color stuff, these blue stuff are basically models. So these are the potential kilonova jet models. So this is something that we have not yet observed. This is again going in the scale of 7 to 8 years after the neutron star merger event. So this is something that is really late time, you can say, or maybe now it's not very late. So essentially, what this means is that if you are, if you were able to see something very brightening because of this dynamical ejecta tail, if it's moving at a higher speed, then obviously at some point you will be able to see emissions from it, right? So if you were able to see something very brightening at late times after the neutron star merger, so this is very interesting. This will lead you to predict the future of the neutron star merger event. What it means is that if you see a very bright radio observation, then it means that after the neutron star merger event, the system did not collapse into a black hole, because black holes cannot produce such bright radio observations. So this means that the system has actually collapsed into a quasi-stable neutron star. So what it means is that if you know a quasi-stable neutron star, or a neutron star, it has its own energy reservoirs. So if it were to form a quasi-stable neutron star, it can pump more energy into the ejecta, and it can make emissions brighter than it would have been in the black hole. So simply by observing at late times and seeing if there is any radio emissions, any brightening radio emissions, you can actually predict the future of the merger. So this is why it's called the merger remnant. So what's remaining after the merger. So I think that is it for the neutron star merger talk, because I think we have covered everything from the start of the neutron star merger to what the merger is. So in conclusion, we learned about the birth of a neutron star merger. We learned about gravitational waves. We also learned about the detection measures. We learned about how multi-messenger astrophysics connects the neutron star merger events, connects basically to our understanding. We also learned about different kinds of emissions from a neutron star merger event, and also we covered the future prospects of the neutron star merger event. So, in conclusion, I would like to thank SEDS Antariksh Club, VIT Chennai. Thank you for giving me this opportunity to present this talk. I would like to thank Kritika Club, IIT Bombay, the Astronomy and Astrophysics Club. Thank you for holding Kritika Summer Project. It really helped me understand a lot about universe. Thanks, very special thanks to Dr. Alessandra Corsi. Almost the entire talk was inspired by her talk, and she had given such an inspiring talk that I immediately knew that I would want to share this information with as many people as I can. And thank you so much, Arvind Balasubramaniam and Kunal Deshmukh, both of whom were my mentors in the summer project that was organized by Kritika. Thank you so much.
That was a great talk, Atreyi. I really enjoyed it. So, to be honest, I didn't know much about, like neutron star mergers on specific, the science behind it, like how do you do? And I'm sure a lot of people have questions. I, in fact, have
Yeah,
few questions.
maybe, I mean, I hope I can do justice because I just told everything that I know.
No, no,
Yeah,
definitely.
sure.
So, we'll open up for questions.
Yeah, no problem.
Sure. I guess everyone can, start raising your hands one by one, and we can start Q&A session. I also saw people interacting in the chat while
Oh,
we
yeah,
were.
I actually didn't.
So yeah, so there are few questions there, but if you'd like to ask it again, you can raise your hand and ask yourself, unmuting yourself, or you can just type in the chat again. So yeah,
Yeah, okay. So just clearing the chat questions. Basically, laser light doesn't go perpendicular. So there's a beam splitter. So laser light is coming as it is like basically the source of the laser light. Essentially, there's a source from which laser light is coming, right? So there's a beam splitter. So the beam splitter is responsible for any kind of light to go in the perpendicular direction. So essentially, this device reflects the incoming laser light into 90-degree angle. So it creates two separate paths just for the reason just so that we can actually kind of detect the intensity. So in general, so it's a basically, if you want to read more about it, this is called a Michelson interferometer. So essentially we see constructive and destructive interferences through this method. So what we do is so there are two mirrors, right? So essentially in a normal Michelson interferometer, one mirror is movable. So if you move one mirror, you are sort of changing the distance, right? So the waves are not lining up and you can see dark and white fringes. So I actually we have this experiment in our college, so it's a pretty cool thing. But the beam splitter is responsible for it to go perpendicular. It doesn't go perpendicular on its own. Yeah.
I think the more simplest answer would be that because the splitter is at 45 degrees, because of
Yeah, it's
Snell's law,
40 degrees.
relatively it becomes 90 degrees. Yeah.
Yeah.
yeah, that's a good explanation. And also I forgot to introduce. So here, like right now, our faculty coordinator Gopinath sir has spoke. So he's a
Not the speaker, you don't need to introduce me.
No, sir, it's fine. So he's our
So,
faculty coordinator for SEDS Antariksh, and he's also faculty teaching physics. So
Oh,
he taught me physics during first semester, and we also learned about the waves and constructive inference, destructive. So it's pretty cool. Yeah.
it is. Physics is really cool. Yeah. Yeah, go on. You can speak
Yeah,
or
you can
yeah,
unmute and speak.
Am I audible?
yeah, yeah.
I thank SETS, Antariksh Club for arranging the seminar. This was very insightful. I thought that I wouldn't be able to understand anything about neutrons. It seems it neutron star and the event, but I'm able to understand it from a very ground level point of view. I actually have two doubts. My first doubt is, although I'm able to understand everything from the overview of the interferometer, I don't think I know the basics of wave physics as simple as interference, because I learned it in 12th and I've completely forgotten the properties of constructive interference and all of these basic things that one needs to be clear to understand the higher order events. So is there something that could you suggest some resources or courses that computer science students uh, can
Yeah, yeah.
use to?
So waves, all right. I read wait, let me let me remember too. So essentially hmm, waves so basically construct, oh yeah, okay, so there's this book Optics, which is Ajoy Ghatak, I think. So by Ajoy Ghatak, there's this book Optics, which actually goes in lots of details about waves. You don't like, you just need to read the first few chapters maybe, but actually in our first in our second year first semester, there was the course Optics, where actually I understood more about waves than I actually understood in 11th, 12th. Maybe that was because of my lack of attention, but I don't know. But yeah, I mean, that was really great. And if you want to, you can follow Ajoy Ghatak. Is amazing. Like, his book is amazing. So yeah, that should be good, I think. But yeah, you just, for understanding interferometer, you just need to, I think, understand the basic constructive and destructive interference, and I think you're good to go. Yeah.
Thank you so much.
No worries. Yeah, go on.
Yes, so I really enjoyed your talk which you gave, and during your talk you once mentioned about the solar mass,
Yeah.
and so accordingly, so what do you think the future of our sun will be? Like, what will happen when it reaches the end stages? Will it become a neutron star?
So that's a very tough question to answer. So essentially, basically, it's in the main sequence phase, I think. Basically, right now, what all stars do right now is converting hydrogen into helium, and eventually, as all stars do, so it will exhaust its hydrogen fuel, causing its core to contract and heat. But yeah, I mean, right now we think, at least we think, that if the mass of the core is around the mass of the sun, or maybe slightly more than the mass of the sun, with our observations, then the system collapses into a neutron star. So I think it's a very safe assumption to have that it will collapse into a neutron star, but again, not sure.
Okay. No way it's going a black hole, right?
Again, I mean, no, I mean, it should be more than 5 times the mass of the sun to,
Okay, okay.
at least with our observations, we have seen that the system should have more than 5 times the mass of the sun. But again, I mean, to be very frank, because of the uncertainties of the equations of state of nuclear matter, we are not very sure about the maximum limit mass of the neutron star. So currently I'm like studying about that. So again, I mean, we're not sure of the mass limit, but yeah, I mean, we really don't know what's between 3 times the solar mass and between 5 times or 6 times the solar mass. We have no idea. Yeah.
Another last question I had, like, neutron star is actually a stage in the death of a star.
Yeah, the
So,
last. Yeah.
so what happens after eventually to the neutron star?
It just becomes basically quasi stable, like again, so there are binary star systems, which if there are binary, most of the star systems are, I think, binary star system. So if it's a binary star system, then because of the gravitational interactions, you can say the two stars may spiral around each other that we saw. Then it can lead to formation of neutron star or a black hole or whatever. So basically, yeah, I mean, I'm not sure. I mean, after a neutron star, potential fate of a neutron star is basically maybe leading to a black hole. That's all. I mean, it. So yeah, like I mean, after black hole, there's really nothing. So yeah, no. I mean, at least we something that we cannot detect. So yeah,
Okay, thank you so much for your answer.
no worries. I don't think so because we don't really know a lot of neutron star mergers. So we are not. I mean, so there's this observable universe which we know, which have its own boundaries. But neutron star mergers have been like not. There have been not a lot of neutron star mergers, and in fact to detect the neutron star mergers, we need to know the celestial sphere mechanics. We need to understand that. How the celestial sphere looks and stuff. So I don't think so. I mean, neutron star mergers have actually not been in a very like there have not been a lot of cases of neutron star mergers as we now know. So in fact neutron star mergers really need gravitational waves to be detected, and gravitational waves were detected first in 2015. So essentially after 2015 we can actually understand the whole neutron star merger event and stuff. So yeah. Yeah, any more questions? Also, thank you so much for I really didn't expect to see so many people after the talk, but thank you so much.
Thank you, Atreyi, for spending your time with us.
Thank you
It's
so much.
wonderful and extremely good to expect from an undergraduate student. And I'm expecting more in the maybe in the following sessions. Maybe we can plan very small range and very focused, small, which is much more, so that it can make it more exciting. So we covered way too many topics.
Yeah, sure. I had lots of fun. Thank you so much for inviting me. And sure, I will share the presentation PDF in the chat. But honestly, there's not much written. I actually explained the most of it. So if I can find resources, I will share that too. So no worries about that. I have one research paper pertaining to this, so I can share that. So yeah, thank you so much.
That sounds really good. So something more I like to add is that Aatreyi actually has her own website that she launched recently, and that has a bunch of resources that you can get into astronomy, get into like the read the books, and how do you go more into this. And she also shared me some other resources on like Python and how do you actually do this. Maybe you could talk more on that, Aatreyi.
Yeah, sure. So yeah, I mean, all right. So essentially, I made a website for aspiring astrophysicists to like start, and so I actually also made a GitHub. Basically, I made a Git repository containing the radio astronomy tutorials, which I did in the project. So I'll share that. I think I shared that with you, Lenin. You can share that in the group. But yeah, I mean, so I believe that for anybody to be going into astrophysics, it's very important to actually understand the data analytic methods because you are actually in at least if you're obviously if you're not very much into theoretical astrophysics, you can always go with that. But if you want to observe or rather observe for yourself and rather form hypotheses or conclusions from the observations, then I think it's important for a lot of people to understand the data analytic methods of astrophysics. So for that, I have actually for me, I mean, I started I think I started in 2023 only. So I started around January or February, and I So I read Python. I mean, I did a course on Python myself. I mean, I self-studied Python and I coded a bunch of it. And then I followed the Kritika Club, IIT Bombay. I followed their Git. So they have an open source Git, so anybody can learn data analysis and in astrophysics. So it's amazing. The resources are amazing. So I studied from there, and then yeah, I mean, that's about it. And in radio astrophysics, radio astronomy, sorry, I made my own tutorials which I have shared, and which Lenin can get all of that to you. And yeah, I mean, that's all I've done actually in Python and astrophysics. Yeah, nothing much to be said.
That's a lot, Atreyi. So thanks a lot, Atreyi. This was a great session. This was very informative for me, and I'm sure you're inspiring a lot of people in this talk. I am very inspired to learn more into this and get with your tutorials, learn more about that. And yeah, I guess we'll wrap up. Aditi, would you like to conclude the session?
Yeah, sure, Lenin. Atri, thank you so much for joining us. On behalf of entire SEDS Antariksh, I'm so grateful that you joined us for this session. And the way you explain things like in such a such brainy things in such a easy manner to us, it's like literally amazing.
Thank you.
And your insights were just valuable. Thank you so much for joining.
Thank you
And
so much
I
for
think
having me.
we can in future we can do more such sessions if you want. Like,
Sure. I'm up for it always. Thank you so
yeah.
much for having me.
Thank you so much, Atri, for joining.
Yeah. Thank you. Thank you, guys. Thank you so much.
Thank you.
Yeah.